All right, so in this chapter, we'll talk about the sense of vision. Yeah. Here's a quote from Benjamin Franklin: "An investment is in knowledge pays the best interest." So, learning is the best skill, best thing to do. Okay, so vision is the most amazing and complex of our senses. So it's and in vision, what you have is you have light coming from an object, and these lenses together, the cornea and the lens together, what they do is, if you have an object like that, they form an inverted image on the retina. There are photoreceptors in the retina. Photoreceptors, what they do is they convert the light falling on the retina into a nerve signal. Those nerve signals are sent to the brain, which is interpreted as an image. Okay? Now, all of us people that are wearing glasses, what is happening is, here's the object, and the image is not forming on the retina. It can either fall in front of the retina for us people who have defective eyes, or behind the retina for whatever reason. Okay? So that's the defect that's happening. All right, so if you want to see it sharp, then then the image needs to fall right on the retina. Okay. Now, here's another thing. On the retina, the receptors have the highest density in this area called the fovea. Okay, so if you're seeing an object here, if the object is here, the image is formed over here. Okay, if the object is here, the image is formed over here. Okay, so the sharpest image is formed when the object is right in front of your eye. Okay, because there the receptors have the highest density. Okay, so your peripheral vision is not sharp. Okay, what you see directly in front of you is the sharpest image. All right. So we'll talk about all of that. Three major disciplines are involved. Physics describes how this image is formed. Physiology describes how the image is processed by the eye-brain system. Yeah. The eye, all it's doing is, what is the eye doing? It's just converting light into nerve signals. Okay. The brain is what's doing the hard work of converting the nerve signals into an image, okay, into a perception in your brain. Perceptual psychology deals with higher level processing, okay, of the information and subsequent formation of a perception. So the information is nerve impulses, and those nerve impulses are converted into a perception of a dog or a cat or whatever. Okay. So we'll talk about the physics in this chapter and a little physiology. Okay. So the first step in the process of seeing is forming a sharp image on the retina. So here's the object, and the first thing you want to do is form a sharp image on the retina. Okay. So you see these light rays pass through many layers of material. So the light rays are passing through air, then they pass through the cornea, the aqueous humor, the lens, the vitreous humor, before it falls on the retina. Okay. Now, here's an important fact. The cornea and lens are treated as a single lens. Okay, so the cornea and the lens are treated as a single lens. So if you refer to your previous chapter, if you have two lenses close enough, they can be treated as a single lens of focal length f. This is f1, and f2 is the focal length of the two lenses. Then the single lens, the focal length of the single lens is given by this formula. Okay, so check your notes from the previous chapter. We've also defined the strength of a lens as S. Smaller the focal length, greater amount it can bend the light, and stronger the lens. Okay. So the strength of the strength of the cornea and the lens combined is the strength of the cornea plus the strength of the lens. Yeah. The cornea and the lens can be treated as a single lens because they are close enough, yeah, with a strength equal to the sum of their individual strengths. And this is a tremendous simplification. So in all the formulas we see, the combined effect is treated as a single lens. Okay? So that's what you'll see in the formula. The cornea is where most of the refraction takes place. The cornea does the most of the bending of the light. It does 65 to 75% of the bending of the light. The aqueous humor, the vitreous humor, they don't do much bending. The rest is done by the lens. All right, so let's say 70-30. Okay, the cornea does 70% of the bending. The lens does 30% of the bending. Okay. So if you have some eye defect, then the image is not forming on the retina, and you want to fix that by surgery, let's say LASIK surgery or whatever. What are you going to fix? The cornea that does most of the bending, you're going to try and fix that. And by the way, you can't fix the lens, you can replace the lens. So what they do is they change the refractive power of the cornea by ablating some cells. They reshape the cornea. So in LASIK surgery, they cut the cornea, fold it back, and then ablate cells from the back. That's one kind of surgery. So they burn cells and then fold it back, and they reshape the cornea so that your image is formed on the retina. Okay. So when vision corrective surgery like LASIK are performed, changes are made to the cornea. Yeah. And like I said, the vitreous and aqueous humor have negligible contribution to refraction. These two guys do not bend the light much. Okay, again, the cornea does 70% of the bending and the lens does 30% of the bending. Yeah. Now here's the deal. Okay, so when you're looking at a close-by object, what's your goal? If your eye is normal, you're forming an image on the retina. Here's a far-off object, and there's a image formed in the retina. Okay. Now the cornea's power doesn't change. So to focus different objects, you have to change the power of the combined object. So what you're doing is you're changing the power of the lens. Okay. So that is called accommodation. Okay. So what you're changing is, so when you're looking at close-by objects, so here's what's happening. So here's your eye when you're looking at close objects. There's the image form. When you're looking at close object, light has to be bent more. When you're looking at far away objects, the light doesn't have to be bent as much. Okay. Okay, so when you're looking at close object, your eye needs to be, the lens power needs to be stronger. When you're looking at far off object, you're not bending the light as much, and so your lens power doesn't need to be as strong. Okay. All right. Now here's again, so like I said, the cornea cannot change its shape. So the cornea cannot change its power. Okay. So when you're looking at the moon and the crystalline lens gets flatter. So when you're looking at far off objects, the lens is thinner because it doesn't have to bend the light as much. When you're looking at close objects, the lens is thicker, so it can bend the light more to form the image. Okay. Now the question is, how does the lens change its shape? Okay. So here's how the lens changes its shape. Okay. So the lens is suspended by a sphincter muscle. This is called the ciliary muscle. It's a sphincter muscle. What is a sphincter muscle? A muscle that joins on itself. It's a ring. Okay. And the lens is suspended from there. Okay. So when the sphincter muscle is relaxed, this is relaxed, the ring is big, these cords pull on this lens, and the lens is thin. Okay. So lens is thin. You're looking at far off objects. So when you look at distant objects, your eye is not straining. Okay. Well, so now you want to read and you want to look at close by objects, so the lens has got to get thicker. Okay. All right, so what happens is, for the lens to get thicker, what happens is the sphincter muscle contracts. That ring becomes smaller. So I'm exaggerating this now. So the sphincter muscle has become smaller. Okay. The sphincter contracted. The lens is thicker. And now close objects are focused. I'm sorry? Yeah, so when the muscle is contracted, the lens has become thicker, and now close objects are focused. So reading strains your eyes. Okay, so that's why they say when you're looking at your computer screen, they tell you to every once in a while look at far off objects. You're relaxing your ciliary muscles. Okay? All right, so here's where eye problems arise. If your eyeball is not the right size, then the image is not formed on the retina. The other way, like you get eye problems, is if your muscles is not completely able to relax, the lens won't get thin enough and you can't see far off objects. That's my problem. That's most of your problem. So the muscle is not completely able to relax, you can't see far off objects. When you have trouble reading, that means the muscle is not able to contract enough, the lens is not able to get thick enough, so you can't read close by objects. So there's the problems. Okay? Yep. So, a good question. So the lens is supposed to be spherical. I'm just cornea. And if it's not, if it's like that causes astigmatism. Okay. So the cornea and lens are supposed to be symmetric, but mostly cornea. It's supposed to be symmetric, like a bowl shape, and if it's not, then you get astigmatism. All right. All right. Do you guys understand all of that? Okay. All right. So the cornea cannot change its shape. When you're looking at the moon, the crystalline lens gets flatter. So when you're looking at far off objects, the lens is thinner. When you're looking at close objects, the lens is thicker. Okay. So Your eye is pretty amazing. You can look around the room, the objects are at different distances, and your eye is instantly focusing on the retina. And so that lens shape is changing instantly. Okay? All this is controlled by the autonomous nervous system seamlessly without your knowledge. You're not controlling it. The result is your eye performs like a very high-end autofocus camera. So your eye is the best autofocus camera there is. Yeah. Every object you look at is always sharply focused. Okay? So if you have a normal eye, any object from 25 centimeters to infinity is automatically already focused. If for young people, they can read from even closer to 25 centimeters. That means their ciliary muscles can contract even more. The lens can get thicker. Okay? And now, as you get older, you lose that contractile ability. So what do you have to do? You have to hold your book further and further away. Okay? All right. So, although the cornea performs the bulk of the refraction, the lens is needed for accommodation. So, the lens is what's changing its focal length to accommodate objects at different distances. The cornea cannot change its focal length. Okay? So, although the cornea does the bulk of the lifting, the fine-tuning is done by the lens, and that's called accommodation. Without the lens, you would not be able to change focus from a distant object to a nearby object. Yeah. All right, so this formula, this is the object distance, which is that. That's the object distance. This is the image distance. Okay, image distance is from retina to there. And there is the focal length. Okay. Now I'll walk you through a problem that you'll need to know. Okay. So make sure we understand this. Okay. So here is the object. Here's the image. So we are measuring distances from here. This, for the adult eye, is taken to be 2 centimeters. That's the average distance. Okay. The closest you can read, so this is sort of not to scale, is 25 centimeters. 25 centimeters is about a foot, a little less than a foot. Okay, that's your reading distance. Okay, so you're designed to see from 25 centimeters to infinity. Okay. So let's calculate the strength of the lens. Okay. The formula is 1 over DO plus 1 over DI equal to 1 over F. Okay. So for close viewing, okay, the object distance is 25 centimeters, which is 0.25 meters. Okay. When we'll calculate the strength in diopters, and those distances have to be in meters. The image distance is 2 centimeters, which is 1.02 meters. And that should equal the focal length of this combined lens and cornea. That should be that. And 1 over the focal length is the strength. So when you're reading, this is the strength you need. Okay, so this is 1 over 0.25 is 4. 1 over 0.02 is 50. So the strength you need is 54. And 1 over meters, 1 is called a diopter. The unit 1 over meter is a diopter. 54 diopter. Okay. Remember, your lens is thicker, your lens is stronger. So when you're reading, the strength of your lens, your eye is 54 diopter. Okay. Now let's looking at far off objects. DO, the object distance is infinity. DI is still 2 centimeters. Okay? So 1 over DO plus the strength. 1 over infinity, that is 0. Okay? Plus 1 over 0.02 meters. So when you're looking at far off object, the strength of the lens is 50 diopter. Okay? All right. So for the normal eye, the strength varies from 50 diopters to 54 diopters. Okay, bigger the number, stronger the lens, the strength. Okay, so you need stronger lens when you're reading close by objects. When you're looking at far off object, the strength is not as strong. Okay? So let's say my strength is 52 diopters to 54 diopters. Okay, so my eye has that defect. Okay, so what can I not see? Yeah, I can't see far off object. Okay, so what do? I go to a doctor, and they give me what is called a diverging lens, okay, a concave lens whose strength is -2 diopters. I can't see far off objects. 52 minus 2 is 50. Now I can see far off object. Okay, so that's what's done. Okay? What if, so that's one example. Okay, what if somebody's strength is 52 to 53 diopters? What's their problem? They can't see close. You go to a doctor, they give you a lens 1 diopter. That's the reading glass. Okay, so, all right, so that's how the fix happens. All right. Okay, so you want to make sure you understand this calculation. There's one problem in the exam, but that's also in the slides. So just pay attention to that problem in the slides. Okay. So when viewing a close object, the eye must be more converging to cause the rays to meet their retina. So again, when you're looking at close object, the sphincter muscle contracts, the lens gets thicker, it gets stronger. Okay, a sphincter muscle action in the eye adjusts the thickness and the strength of the lens, doing the fine tuning necessary to produce an image precisely on the retina. The sphincter muscle is relaxed and the lens is thin when looking at far off objects. Okay, so relaxed when you're looking at far off objects. The muscle is tensed when you're focusing on nearby objects. Okay? And the lens strength is stronger. So distant vision, therefore, is termed relaxed, and near vision is accommodated. Okay. You guys understanding this? I'm not going too fast? Okay. Okay, so the average adult distance from the retina to the lens is 2 centimeters, which is 0.02 meters. Okay, that's what we've been taking for the image distance. Okay, so for normal vision, you're designed to read from 25 centimeters, just under 1 feet. You can read up to there. Younger people can read from closer because their muscle can contract even more. Okay? And then we are supposed to be able to see up to infinity. Okay? I can't see beyond this point without my glass. Okay? So the normal strength is from 50 to 54 diopters. Okay? And again, remember, diopters is, so I'll spell that. Okay, 1 diopter is 1/1 meter. Okay. So this goes through the calculation. So this is 50 diopters when you're looking at an object that is at infinity. Okay. So when the object distance is infinity, that's 0. Okay. And 54 diopter when the object distance is 25 centimeters, 0.25 meters. Okay. So how do you change the strength of your lens from 50 to 54 diameter? By changing the strength of the lens. You don't change the strength of the cornea. Okay? So the maximum strength of 50 diopters, okay, is only 8% greater than 50 diopter. Okay, so you're able to change your strength by about 8%. Okay? Accommodation ability is usually better than 8% when the person is younger. So it can be more than 54 diopter, so younger people can read closer than 25 centimeters. Okay? But as you age, you lose that range. Okay? So accommodation ability decreases steadily with age. Okay? So as you grow older, you have to hold your book further and further. Or else you need reading glasses. Yeah. Okay. So now we'll talk about visual acuity, meaning how sharp the image is. Okay. The sharpness is decided as follows. If you have 2 dots, and if you're able to see 2 dots, then you have resolved the image. Okay? But if you have 2 dots and all you're forming is 1 dot, all you're seeing is 1 dot, then you haven't resolved 2 points. Okay? All right, so the human eye can resolve points with a minimum angular separation of 3 times 10 to the minus 4 radians. That's this angle. Okay? If these 2 dots are apart by that angle, that many radians, then you can tell them as 2 dots. And that translates to 1 minute of an arc. Okay. By the way, how many degrees in a circle? I'm sorry? 360 degrees in a circle. Sometimes a degree is too large an angle, so 1 degree is divided into 60 minutes. Okay. And oftentimes 1 minute is too large, and then that's further divided into 60 seconds. Okay. So a minute is 1/60th of a degree. Okay. That's how. So if 2 objects are separated by 1 minute of an arc, then your eye can tell they're 2 objects. Okay. So here is that in real language. Humans can resolve details as small as the diameter of a human hair at arm's length. At arm's length, if 2 dots are apart, the width of a human hair, you can tell them apart. Here's a larger example. I don't know if you've experienced this. If a car is far, far away, you can't tell if it's a motorcycle or a car, right? Okay, so it turns out that a car has to be, it can less than 2.5 miles, and then you can see 2 headlights. If it's 3 miles away, then you are not able to resolve, and it appears as a single light. Okay, so that's that 1 minute of an arc in a different language. Okay. So that's your visual acuity. Okay. All right, what is going on in the retina? Okay. So for your brain to be able to tell 2 spots, what needs to happen is these 2 dots, images, need to, so on your retina, here are these cells that are detecting the light. If that dot forms on this cell is sending a nerve signal to the brain, and the other dot falls on there, then you can tell them there are 2 separate dots. If they form on, if the other dot falls on here, then your brain thinks that there's a single dot. Okay? So that's visual acuity. Okay? So for the eye to resolve two dots, their images must fall on two non-adjacent cells on the retina, okay? As shown. If the images of the two dots fall on adjacent cells, if they fall on this cell and that cell, then they are interpreted as a single large dot.
Can they fall?
I'm sorry?
I said, can they fall any other way?
Oh, yeah, they can fall here, and then you're easily able to tell. Yeah. So you have to have at least one gap. So if you want to increase the sharpness of your image, what do you have to do? What could you do? No, well, let's say you get to design a human eye. Okay? How could you improve the visual acuity? Put more cells, put smaller cells. Did you guys understand that? Right? If you put more cells, and now, so if the cells are closer, you can form an image here and an image here, and then you can tell them apart. Yeah? So the density of the cells, if you increase the density of the cells in your eye, then you can see more sharper image. That's what happens in eagles. Eagles have 5 times the density that we have. So an eagle has essentially eyesight 5 times more acute. Okay. Now, it turns out that, so we talked about the fovea. Okay, so let me go there. Okay, so this, in our eye, only this region has the highest density. That's called the fovea. It has the highest density of cells. So when the image is formed over there, that's when you can see the sharpest. Okay, so I can see sharp images that are objects that are directly in front of my eye, because that image is forming on the fovea. Her image is not sharp because her image is falling on the right of the fovea. Okay, and that window is not sharp because that image is falling on the left of the fovea. Okay? All right. All right, so here's the language of the optometrist. Okay. If you have 20/20 vision, okay, this number refers to you, this number refers to the average person. Okay, if you have 20/20 vision, or this refers to normal vision. Somebody with normal vision, they can see from 20 feet, you can see from 20 feet. Okay? If you have 20/40 vision, somebody who can see from 40 feet away, from here to the wall, you have to be 20 feet away to see that. So you have to go half the distance. So when this fraction is smaller than 1, your vision is worse. If you have 20/15 vision, a normal vision can see from 15 feet. You can see that from 20 feet away. You're a champion. Okay? So that's what that means. Okay, so the fovea is the small pit in the retina, okay, with a high density of cells. And by the way, those are cone cells. We'll come to that in a little bit. Cone cells see colors. Okay. Cones see colors, and rods, black and white. Yeah. So we have a small region on the retina that can give you a sharp image. The fovea is densely packed with cone photoreceptors, which allow for color vision and high visual acuity. Okay. So the fovea provides exceptional visual acuity. It only covers a small area in the visual field. Okay, why don't we have a high density of cells all over the retina? Why don't we have sharp peripheral vision? Why do you think that is? Well, if you send too much information to the brain has to devote a large area part of itself to vision. You know? So it's a resource management issue. All right, now let's talk about the eagle. Eagles are generally considered to have the best eyesight in the animal kingdom. Okay? Eagles' eye are roughly the same size as humans. Okay? The size of an eagle eye is the same size as, and they're, I don't know, probably an eagle is 10 pounds. So 15 times lighter, you know. Eagles have 25 vision. Okay, what we can see from 5 feet, the eagle can see from 20 feet. Okay. So here's how it does that. Remember, if you have sharpness of image, how do you sharpen your image? You got to pack that fovea with high density of cells. That's how you improve your sight. Okay. So an eagle's central fovea has over 1 million cones per square millimeter. A square millimeter is that much. Okay. While the human's fovea has only 200,000. Okay. All right, so its density is 5 times greater. In addition, the eagle has 340 degrees of vision. And the human has a little over 180, about roughly 200, okay? This region is binocular vision, okay? We'll talk about it. Binocular vision meaning you have depth perception in this region. So the eagle has depth perception in a smaller region. But then, you know, you want better depth perception, you just turn your head. Okay. So eagles have 340 degree fields and ours is about 200. So here's a better image. So we have binocular vision in 120 degrees of our field of view. Okay, what this is okay, this region is uniocular, meaning this region we can only see with our right eye. This region we can only see with our left eye. Okay. So binocular vision, an animal has 2 eyes capable of seeing in the same direction. Okay, so we have 2 eyes. And the reason we have 2 eyes is we have pointing frontwards, we can have a larger field of view and we get depth perception, precise depth perception. So those are the 2 reasons why we have 2 eyes. Okay. So in principle, with 1 eye, you wouldn't be able to get depth perception. But our brains are smart. What you do is if you were born with 1 eye, you would get depth perception by moving your eye around. Having 2 eyes rather than just 1 gives a wider field of view. Yeah. So we have approximately 200 degree field of view. Yeah. 2 eyes give stereopsis, that's the technical term. Different positions on the head gives precise depth perception. Okay. All right, so here's how we get depth perception. So if you're looking at close objects, you see this eye has to turn inward and this eye has to turn inward. And muscles make the eye turn. And the amount of effort put in by the muscle, that information is sent to the brain. The more effort you're putting in, the closer the object. Okay? If an object is far off, your muscles are not having to work as much to turn the eye, the object is far off. Okay? When the 2 eyes focus on the same object, they will angle inward toward each other, and that's called convergence. Okay? Depending on the distance of the object, the eyes will converge more for close-up objects or less for distant objects. The extra effort used by the muscles on the outside of each ball gives a clue to the brain about how far the object is. Yeah. Okay, so vision correction, myopia, meaning nearsightedness. If you're nearsighted, what that means is you can see close by objects, you can't see far off objects. Okay, to see far off objects, to see at infinity, your ciliary muscle needs to be relaxed, your lens needs to be thinner. So if you can't see far off objects, your ciliary muscle cannot completely relax. Okay. So what happens is, so for nearsighted people, for far off objects, the image is formed in front of the retina because the lens is too thick and it's bending the light more and it forms the image in front of the retina. Okay, so if you're nearsighted, the image is formed in front of the retina. If you're farsighted, meaning you can look at far off objects but can't look at nearby objects, the image is formed. If you can't see nearby objects, you're not contracting enough, your lens is not getting, and the image is formed behind the retina. So nearsightedness and farsightedness are the two problems, most common problems. The cause of both defects can be either a lens of incorrect strength. Okay, so what is the normal range for strength? 50D to 54D. Okay, so if it's 50D to 53D, what is this problem? This is normal. And this is you're not able to see close objects, so this is farsighted. And 52D to 54D, you're able to see close objects, you're not able to see far objects, so nearsighted. Yeah. Okay, so your defects, the cause of both defects can be either a lens of incorrect strength, okay, or small perfections such as an eye that is 0.01 centimeters too long. Okay, so your eye size, 100th of a centimeter, that's 10th of a millimeter. A millimeter is that much. A 10th of a millimeter off on the size of the eye. Yep.
So what happens to like light and cones and rods if you're like blind? You just don't have cones and rods? Do you lack them?
Probably it's the wiring. Normally it's the wiring that's cut, I think.
The light,
So
doesn't get absorbed?
no, the cones are doing the job, but that electrical signal is not being sent by the optic nerve if your optic nerve is damaged. You know, yeah, so the signal has to be transmitted to the brain. So you can have an optic nerve, and so let's say the visual cortex is removed for some reason in the brain. You can't see it. Okay. Now the brain, of course, is very adaptive. Other parts of the brain will take over the job. But anyway. Okay, so nearsighted eye can see close objects clearly, but distant vision is blurry. So their strength is, let's say 52D. I'm just putting up examples. Okay, you can't see. You need 50 diopters to see distant objects. Okay? The strength of the lens is greater than 50 diopters. Okay. The myopic eye cannot relax enough to avoid converging rays from a distant object. Okay, so in the myopic eye, so when you have parallel rays, this object is at infinity. You see the image is formed in front of the retina. Okay? The muscle is not relaxed enough. It's not become thin enough to focus it on the retina. So you give a diverging lens, okay? And this has a negative focal length. Focal length is negative. Okay, strength is negative. So to correct this, you give a strength of minus 2 diopters. To correct for myopia, diverging spectacle, a lens of negative strength is used. A far-sighted eye, for a far-sighted eye, you can see far-off objects, but if a close object, this is a normal eye, for a far-sighted eye, you can see objects fine. A close object, the image is formed behind the retina. Okay. So for a far-sighted eye, let's say this is the range. Okay. You cannot see close by objects properly because you cannot increase the strength of your eye to 54 diopters. Okay? So what you do is you give a converging lens of strength plus 2 diopters here in this case. Okay? Plus 2 plus 52 is 54. And now you can see close by objects. For an eye of normal length, this means that the maximum strength of the eye is less than the 54 diopters needed. To correct for hyperopia, a converging spectacle of positive strength is used. Okay. So here's a problem you want to be aware of. So when you're looking at an object 1 meter away, the strength of your lens is 51 diopters. So here's the astigmatism that we talked about. Okay. In astigmatism, another very common vision defect, the cornea or the lens of the eye is not symmetric. Okay. So if it's supposed to be bowl shape, it's a dented bowl. Okay. And you can test for astigmatism here using this diagram. Okay, so what you would do is you check each eye separately and look at the center of the cross. So what you do is cover each eye, look at the center of the cross, and if any of these lines appear brighter than, some lines appear brighter than others, then you have astigmatism. Okay? If they all appear equally bright, then you don't have astigmatism in that eye. Okay? So astigmatism often can be corrected by using spectacles lens with opposite asymmetry. Okay? So if you're, let's say, instead of a bowl, if your eyes are like a cylinder, then you take the opposite cylinder and correct it. All right, so rods and cones. Rods do black and white. And cones do color vision. Okay. Cones are mostly around the fovea, and the rods are, there are no rods in the fovea, okay? And the rods are distributed in peripheral vision. Okay. So they're both photoreceptors. What does that mean? A photoreceptor converts photons falling on them into a nerve impulse. Okay? So it converts into an electrical signal. Convert the energy contained in light photons to electrical signals. Okay. You have 130 million rods, okay, throughout the retina, except for a small region in the center of the fovea. Okay, so except there, you have 130 million rods distributed all over your retina. They're more sensitive than cones. In fact, they're about 500 to 1,000 times more sensitive than cones. And they're solely responsible for vision in the dark environment and for peripheral vision. Rods do not yield color information. Color vision is associated with cones. You have 7 million of those, 130 million rods and 7 million cones. You have 3 types of cones. So you have a cone that responds to blue light, you have a cone that responds to green light, and a cone that responds to yellow light. And between these 3 cones, in normal vision, you can see about a million hues. Okay. Each of these guys have 100 different levels of excitation. So 100 for the blue, 100 for the green, 100 for the yellow, and that's a million. Okay. So you can see a million hues. Okay, shown is the absorption characteristics of the three cone pigments in humans. About 8% men and 1% women are partially colorblind. Most of them are missing only one type of cone. So color blindness is if you're missing one type of cone, then you don't see that combination. So instead of 1,000,000, now you're seeing 100 times 100, 1,000, 10,000 shades, not 1,000,000 shades. Okay? There are also rare individuals that lack all three types of cones and are totally colorblind. Okay, and so they also don't have as sharp an image because fovea is where the cones are, and rods are photoreceptor cells in the retina that help with low vision light. They convert photon into electrical signals. They're responsible for black and white vision in low light. So rods are responsible for black and white vision in low light and peripheral vision. So rods are concentrated in the outer retina. Their density increases towards periphery. There are no rods in the central fovea. So here are the rods, here are the cones. Rods are 500 to 1,000 times more sensitive than cones. Yeah. They happen to be most sensitive to blue-green light. Yeah. And their peak sensitivity is around 500 nanometers. Rods have slow response speed, low spatial acuity, meaning their density is not as high as 200,000 cones in the fovea per millimeter. They cannot function during the day because they're photo-bleached. Okay? They're saturated during the day. So rods are for night vision. Okay? Rods evolved about 500 million years ago to help organisms survive in low light environment. Okay. So a simplified theory of color vision is there are three primary colors corresponding to maximum sensitivities of three types of cone. The hundreds of hues that the eye can distinguish are created by various stimulations of two or three of the cones. All hues that can be reproduced by adding three primary colors together in various proportions. Okay, where is that? Okay, so so here is the response of one of the cones. Here is the response of the other cone and the third cone. The average human can see around 100 million different colors. This is because the human eye has three types of cone, each of which can register about 100 different color shades. Okay, so what that means is, let's say each of these cones can be excited from a level of 1 to 100. So let's say the blue cone, gets excited to 50, 40, and 30. Okay, so some light falls on your eye. This guy got excited to 50, 40, 30. These numbers are sent to the brain, and the brain interprets that as a color. Okay? And since each of these guys can take values from 1 to 100, 100 times 100 times 100, that's 1,000,000 different shades. The average human can see around 1,000,000 different colors. Okay? I don't know if you know anybody like this, but some people have 4 types of cones. Okay, so they'll have a 4th cone, an additional orange one. This allows them to see 100 million shades. Okay, so normal humans see 1,000,000 shades. These people see 100, and it's a sizable population, over 1%. So 1 in 100. The human eye can perceive more variation in warmer colors than cooler colors. So we see warmer colors more. Okay? That's because almost 2/3 of the cone process longer light wavelengths. Color blindness can occur when one or more of the cone types are not functioning as expected. Hmm? The most common types of color blindness are red-green color blindness, okay, followed by blue-yellow. Okay, so red-green, if one of these guys are not functioning properly, then you have that kind of color blindness. Okay, so here's how colored objects work. So when you're, oh, by the way, I keep changing slides a little, but I don't know if you have this, that old diagram was not, yeah. Okay, so here's how a red object works. This is white light falling on it. So sunlight is white light. When you're looking at a red object, blue and green are absorbed, only red is reflected. And so that's how you see red. Okay. So an object's color is what color it's reflecting. Okay. So here's an interesting part. What color are plants? Green. So they reflect green light. Okay, they cannot absorb green light. They absorb all other wavelengths. What do plants do? They use energy from sunlight and produce food. So now if you try and grow a plant only in green light, you kill them because they can't absorb that. Yeah. So if you take a green filter in a greenhouse and just shine green lights on that, okay? White objects reflect all wavelengths equally well, and black objects absorb all wavelengths equally well. Yeah? So gray is partial absorption of all wavelengths. So true color is perhaps more accurately defined as the reflecting characteristic of a substance. So the color is more a reflection characteristics of the substance. Okay. All right, guys.